Alright, there are a couple of ways to try to find the angular velocity, or the final angular velocity of a discus thrower who revolves a disc around one full revolution in a period of time of 1 second. The first is the basic way. A couple of basics. Remember that when we go from kinematic to rotational, x is equal to theta, or translates to theta. V translates to omega, velocity translates to angular velocity. Acceleration, angular acceleration, that's an alpha, by the way. And time, of course, is still time. Either way, in both cases, we're still trying to find the final angular velocity, or how fast it's going at the end. So the first thing we need to do is find an equation that has omega f in it based on our list. First of all, we have time equals 1 second. It goes around one revolution. And because that's telling you how far he's going around, instead of using x, we're using theta. So theta is equal to 1 revolution. And then if we multiply that by a conversion factor, we can find out that it's equal to 2 pi radians. So we know theta equals 2 pi radians. We know the initial velocity, the initial angular velocity, is equal to 0 because he's starting from rest. We know the time period is equal to 1 second, and of course we want to find final angular velocity. So then we look at our equations we have for angular velocity. From the equation Vf equals V naught plus At, we can translate that to omega f equals omega naught plus alpha times time. And we know that omega naught is 0. We have time. We want final angular velocity, but we don't have alpha. So in this case, you would have to solve for alpha first. So we have to find another equation that has alpha in it. And from there, you can start with theta equals theta naught, or you could have called it delta theta equals, same idea, plus omega naught t plus 1/2 alpha t squared. And that comes from x equals x naught plus v naught t plus 1/2 at squared. Same idea. We're just translating from kinematic to rotational. So then we start plugging it in. We know the initial position is 0. The final position is 1 revolution, which, as we discussed here, 1 revolution is equal to 2 pi radians. So 2 pi radians equals omega naught, but we also know that that's 0, so we can get rid of that. And then we're left with 1/2 alpha times time, which is 1 second, squared. So then we just do a little math to solve for alpha, and we find that the angular acceleration, alpha, is equal to 4 pi radians per second squared. And remember, your units for acceleration were meters per second squared, but now we're using radians per second squared. So that's our answer for alpha, but we weren't trying to find alpha, we were trying to find final angular velocity. So then we can bring this equation that we had before. Vf equals V naught plus At, omega f equals omega naught plus alpha t. So then we plug it back into there now that we have alpha, and we can see omega f equals omega naught plus At, or alpha t, excuse me. But remember, omega naught is equal to 0. But we have alpha, we have time, so we can plug these in. Alpha was equal to 4 pi radians per second squared times our time of 1 second. One of the seconds is going to cancel out, and then you're going to find a final angular velocity of 4 pi times 1 is still equal to 4 pi radians per second. And remember, our units for velocity when we were doing kinematics were meters per second, so now we have radians per second. It's the same idea. We're just translating everything back and forth. Now, method 2 is much easier. So if we're trying to find the final angular velocity, we realize that based on the acceleration, he starts from 0, so omega naught is still 0. We want to know the final angular velocity. And let's assume that we haven't done all of this and we don't know acceleration yet. But we know his average velocity is going to be exactly equal to half of his final velocity. And his average velocity is equal to his final velocity plus his initial velocity divided by 2. Average, beginning plus end divided by 2. Assuming it's a constant acceleration, which it says he is. So from here, if we can figure out the average angular velocity, how far and how much time, we can very quickly solve for that because solve for the final angular velocity, omega f, because we know the initial angular velocity is 0. So we're left with the average angular velocity is equal to the final angular velocity divided by 2. And then, of course, you just bring the 2 to the other side. 2 times the average is equal to the final angular velocity, which is exactly the way it was in kinematics. The final velocity is equal to the average velocity times 2. Assuming they start from rest. Assuming they start from rest. So then we plug this back in, but we don't know the average angular velocity. But it's very simple. It's just distance divided by time. Or, in this case, theta divided by t. And we know that theta, we already said, was equal to 1 revolution, or 2 pi radians. So bring down our 2. 2 times the average, which is theta over t, equals the final angular velocity. 2 times 2 pi radians, which was our theta, over time, which was 1 second, equals omega f. So then you multiply through, and what do you get? 4 pi radians per second. So no matter which method you use, you should get the same results. So then we go with 4 pi radians per second. Again, radians per second, 4 pi. No matter which method you use, as long as you use the same principles, you should get the same results and have the same answer. Thanks.